Welcome back. I hope your Halloween was wonderful. I think I counted. Well, I didn't really count. I just saw how much candy I had left. We had a boatload. It was wonderful. Lots of little goblins and scary things coming to our door. I think I gave away 150 people. Halloween's my favorite time of the year because I get to put out lights and they get to flash and all the scary sounds and sights. But today we're going to talk about threshold detection, and we're going to violate the first rule of OpAmps. Remind me the first rule of OpAmps. The first rule of OpAmps. This one. Remember this one? Negative feedback, okay? This is positive feedback. Upside down, trying to balance the thing, it doesn't work because any small change makes it go unstable. And this was our negative feedback. Any small deviation from center caused the force to have it go more stable. But today we're going to use positive feedback for good, okay? And in particular, we're going to use an OpAmp in a mode called threshold detection. Okay? So I'm going to have a signal which comes into a module, and then I'm going to have a binary output. Right? So if this is my input, I'm going to have a 3.3 volt output if Vin is greater than some constant. Okay? And I'm going to have another signal like 0 if Vin is less than that constant. Okay? And in order to build this circuit, I'm going to use positive feedback. The essence of what we're going to do is to use an OpAmp either with no feedback or positive feedback. And if you remember the rule, right, the rule of the OpAmp, the way this works, okay, if this is my input voltage and this is some constant like 2 volts, okay, what was the fundamental equation, the linear equation that related the output to the inputs? You remember that? It was some very large amount, some very large number, times the difference between right? That's what the OpAmp is trying to do, to take the input, subtract off the other side, and then multiply it times a large number. So if the input were 3 volts, what's the output? 200,000. Can't get there, right? So what's going to happen to the output? It's a rail-to-rail OpAmp. That rule we can't violate. So what is the maximum output that this thing can generate? 3.3 volts. So rather than going to 200,000 volts, it's going to go to 3.3 volts. Similarly, what happens if the input were 1 volt? Okay? If the input were 1 volt, right? And now we're trying to generate this waveform. Okay? It's going to try to get to 200,000 volts. It's not going to get there. How far is it going to go? It's going to go down to 0. Okay? It's going to go to 0. And at some point, it's going to, any voltage that's really close to 2, but larger than 2, is going to saturate. And any voltage that is close to 2, but less than 2, is going to saturate down to 0. Okay? And that is the essence of the equation, the circuit shown here. Okay, so if the threshold voltage is 2 volts, then the output is going to switch. This actually, let me build one here, see if you can tell me what this is. Okay, assuming this is powered with 3.3 volts down to ground. What did I just build, by the way? If the input were 0, what is the output? Okay. Which is bigger, right? If the input were 0, okay, which is bigger, 1.5 or 0? Right? It's not going to go to 350,000 volts, is it? Right? It's just going to go to 3.3 volts. What if the input were 3.3 volts? What's it going to do? You see what I built? What's it going to do? It's going to go to 0. Okay? And I just spent $2 making what? A NOT gate. Okay? The cool part about this circuit, this whole field of circuits, okay? This whole field of circuits that follow this pattern is that they have analog inputs, which means it can exist at any voltage between 0 to 3.3 volts. Any voltage in that range is acceptable. But what does it create as an output? I mean, look at the way if this is an OpAmp right here, which either has positive or no feedback, what can you tell me about the output? It's going to be what or what? 0 or 3.3. And what's the definition of such a signal? It's digital, right? So what I just created was a class of circuits that fit into analog inputs and digital outputs. Okay? So what we're going to use this for, we're going to connect this up to our timer and use input capture to measure period or pulse width or frequency, and have a signal that exists over here that can vary in amplitude, but create an output which is digitally compatible to my microcontroller. So I can either say, well, is it snowing outside? I got a snow sensor, and then out comes the snow sensor, and I'm going to have a rising edge when it starts to snow, and then my interrupt's going to happen, or I'm going to use input capture to measure the length of the snowstorm, or whatever. I'm going to be able to connect this up to a digital signal, digital ports. This is a very important class of interfacing, okay, that allows us to take things that, like in this case on the right, the input is analog, and embedded in that is the period of something interesting, and we just roll it through this OpAmp with the appropriate threshold voltage, and out comes a beautiful square wave at that same period. Okay? Something really bad happens if I zoom in to that waveform. All right, something bad happens. Let me zoom way in. And this is my input, okay? And this is my output. See that? Okay? Okay. Let me zoom way in, black, and add some noise. And let me draw the thresholder. There we go. Only get a couple of glitches. And now let's draw the output. Okay. But if I'm measuring period or frequency or generating interrupts, this glitch is unacceptable. Okay? It's unacceptable. So what I'm going to do is, let me give you an analogous problem. Okay, you got an air conditioner in your house. What temperature would you love it to be? Your favorite temperature? 75. Okay, he's not paying the electric bill. Okay, just saying. Where do you have to pay the electric bill? 75 degrees F. Okay. Okay. So and the F, not C. Yeah, fine. Yeah. There we go. Sorry. F. Sorry. And this is the actual temperature. Okay? And the analogous problem is this is the if it gets too hot, here the AC is on, and here the AC is off. Right? That's the analogous problem here for the threshold detector. And what happens right there is you're going to burn out the relays. Okay, because it's going to go boom, and then you got to call up, spend $200 and get it fixed. Okay, so how does your air conditioner actually work? By the way, everybody stayed there and watched it. What does it do? How does it protect itself from the stupidness, which is this thing? How does it work?
Does it only look at inputs periodically?
Mm-mm. No, then it would be Wednesday is the only day it gets cool. No, you can't slow down. You can't slow this down. Okay, if it's too hot, I want to come on. If it's too cold, I want to go off. But what does it actually do?
Hysteresis?
Yeah. Okay, that's a fancy word. He said hysteresis, and that's the right answer. But tell these fine folks what that means. Hysteresis is the answer to the question, but it's the complicated answer. But what's the 5th grade answer to how this thing works? There are two things here. Okay, you just should watch your air conditioner. Okay, when does it turn on? Okay, it's at a threshold. Okay, we are going to create a second threshold. Okay, and the rule will be, okay, turn on if it goes above 77. Okay, that's going to be the rule. So, green. Okay, we are going to turn on if it goes above 77. Okay? And we're going to turn off when it goes below 75. Oops, I want the black one to do that. Okay, so what I'm going to do is turn it off when it goes below 75. And that is the essence of hysteresis. Two thresholds. One to turn it on and one to turn it off. So right there at the junction of on and off, it doesn't oscillate out of control. Okay, that's the essence of what we're doing here. But now we've got to build it. Okay, we've got to build it. The way we're going to build it is with positive feedback. Okay, the positive feedback is going to allow us to create this activity. Okay, so let's erase Control C. Black. Okay. This resistor is optional. Okay. In order to understand how hysteresis works, we need to sort of have a sort of corollary to one of the other OpAmp rules. Okay. And that was something interesting happens. If we call this Vy and we call this Vx, something interesting happens when the two voltages are equal. You remember negative feedback caused them to be equal. Okay? But here in positive feedback, they're not going to be equal. But something interesting happens when they are. Okay? When they are equal, that's when it switches. That's when it flips. That's the time in which it will flip the mode and cause the output to go from 0 to 3.3 or 3.3 to 0. Okay? So that's the interest. So we're going to look for the point at which those two are equal. Okay? Again, they're not going to be equal, but when they are equal, that's an interesting spot. Okay? The other op-amp rules are interesting. IY equals 0, IX equals 0. That's still no current into the op-amp. So what can you tell me about Vx? Right? It has to be equal to the input voltage. Okay? And so now, what can you tell me about Vy? Again, there's no feedback here, but we have something which is Ohm's law-like, okay? But it depends on what? It depends on the output. So I'm going to have to do Vy twice. I'm going to do Vy if the output is high. So if the output is equal to 3.3 volts, okay, then this voltage here is a voltage divider, right, which is 2 plus, right, 2 plus something. You see that? It's going to be 2 plus something. Okay? I want to know the current through this resistor, right? The current through this resistor is 3.3 volts minus 2 volts over 10K. You know? That's the current through that resistor. And then I'm going to add or multiply that times the 10K, multiply that, oh no, plus 100K, sorry. Times 10K. See that? But the point is, this Vy, what is Vy relative to 2? It's bigger, okay? And it's bigger by the ratio of the 10K to the 100K. Okay? What if the output voltage were 0 volts? What happens? If this is 0 volts, okay, what can you tell me about the Vy? It's going to be less than 2 volts, right? Right? So if this is 0, then this voltage here is going to be 2 volts minus the amount of current, which is 2 volts minus 0 volts over 110K, right, times 10K. So again, the amount of the difference between the 2 volts, which was my threshold. This is my threshold voltage, 2 volts. I have 2 thresholds. Okay? And what's going to happen is, as it goes over, if you think about it here, when do I use the threshold at 2 plus delta? If what? I'm going to use 2 plus delta. If what? Right? If the output is already 3. And I'm going to use 2 minus, actually it's a different delta, if the output is at 0. If I were to remove the resistors, right, altogether, this behavior does what? What is the overall behavior of this system? What is the input-output relationship? Right. So if without the resistors here, the input, if the input were positive, what would be the output? Right. If the input were 3 volts and there were no resistors, what would be the output? Look at that. 0. Right. So this guy has got the NOT gate behavior, right at 2 volts. Okay. But once I add the resistors, okay, again, if the output is already 3 volts, okay, it's going to have this curve. It has to get bigger than 2 volts for it to switch. But if the output is already 0, it's going to be, the threshold is going to be 2 minus that delta. Okay? And that's the essence of how your air conditioner works, is the essence of hysteresis. And this hysteresis value, the value in which it hysteresis is at, okay, is a function of the difference between the threshold and the 3 and 4. Look at, here's the equation right there. The difference between the thresholds, okay, and the 3 and 0. There's one, here's the other. And the ratio of the resistors chosen. So if I want a bigger hysteresis, I'm going to make the resistors close to each other. I want a smaller hysteresis, I'll make them different from each other. Yeah, this is essentially that circuit with an actual threshold in there. Okay? And again, the ratio of these resistors will determine the total amount of hysteresis that I can generate. Right? So in summary, we can use positive feedback. We still have all the rules but a couple that we had before. We're going to use positive feedback. We're going to use good op-amps. No current into the op-amp, but what we're going to get is a rail-to-rail. So the V-out is either going to be 3.3 volts if Vy is bigger than Vx, or it's going to be 0 volts if Vy is less than Vx, where Vx and Vy are the voltages that are actually on the device. Okay? That's essentially what it is. And we're going to see this in Lab 10 because we'll have a tachometer, which is be the noisiest thing you've ever seen. Questions on this? All right. So some of the sort of the catch points when you're doing the exam or you're doing life, we want to decide whether we want a linear circuit like we did in the last couple of lectures, or do we want this threshold detector, which by its nature is nonlinear.